My name is Matthew, and in this video we're going to talk about applications of Extrema. And in this conversation, since in the previous video and in the previous section of this particular book, we already talked about how to find absolute maximum and minimum points, both the x values and the y values. And this section is just about applications of that topic. What I thought we could do is go in and just look at a handful of homework problems that I'm going to be assigning to my students. And these problems go along with Stewart's 8th edition calculus book, and these problems exist in WebAssign, which is produced by Pearson. And so many thanks to them for these problems, which will hopefully be good illustrations for you. In the first problem, and I've got this kind of zoomed in large because in order to get access to all the steps in this problem, I had to click a little checkbox that said, show the entire problem worked out with solutions. So I don't want all the solutions on the screen. So for the moment, we're going to just do a little scrolling from left to right in order to get our eyes on the entire setup of this problem. And the setup here says that we're going to follow some steps, I think it's A through F, to find the non-negative numbers x and y, so that's going to be important, that satisfy the given requirements. And we'll get back to those requirements in a second. And then ultimately we want to give the optimum value of the indicated expression. And we're going to complete parts A through F. Okay, so what are the givens? The givens are this. We know that x plus y is equal to 210, and we want the product where p is equal to x times y, so x times y is the product. We want that to be as large as possible. And the first, this is sort of like a guided solution kind of a problem where we're prompted to go through the process. And part A asks us to take that x plus y equals 210 equation and solve it for y. That's pretty straightforward. We subtract x from both sides. Part B asks us to substitute that result into the equation p equals xy. So now I know, or now that I know that y is equal to 210 minus x, I'm looking at the equation p equals xy, and I'm replacing that y value with 210 minus x. And right in the bottom left corner of the screen, you're seeing that the 210 minus x is written in parentheses. And when we do substitution like that, it's a good idea to put the new value or the new expression in parentheses. So again, in the bottom left corner of your screen, you're seeing p equals x times y, except the y has been replaced with what y equals, namely 210 minus x in this version of this problem. And the real reason why I wanted to do, or to look at this problem with you, is because part C asks us to find the domain of capital P. And that's a little strange because if we were to look at the answer in part B and distribute and move the two terms around, we would end up with negative x squared plus 210x, which is a polynomial. And polynomials have a domain that consists of all real numbers. So how am I supposed to be giving some kind of a domain? Here the domain is 0 to 210. How am I supposed to get that? Where'd that come from? I can, if I'm doing my own version of this problem, the first number is probably 0, and the second number is whatever your version of 210 is. But where did those come from? They came from this. Remember I said that was kind of important. Near the top right corner of the screen, you're seeing in the instructions, follow the steps below to find the non-negative numbers x and y. So if x is going to be non-negative, that means it could be 0 or greater. Okay, so how are we capping it at 210? Well, we want our y value to also be positive. And the answer to part A says that y equals 210 minus x. If I want my y value to stay positive, or to be non-negative, the smallest my y value wants to end up being is 0. As my x value gets larger and I'm plugging it into the answer to part A, I've got y equals 210 minus, well, 210 minus 0 is still 210. That's positive. My y value is still positive. Great. As my x value increases, let's say our x value is 209. Now y equals 210 minus 209. Now my y value is only 1. And when my x value hits 210, y equals 210 minus 210, which is 0. And we don't want our y value to go any lower than 0, which means that our x value has to be capped at 210. If x is any larger, it's going to push y into the negative values. So that thought process is how this answer in the bottom left corner, the domain of capital P, was determined. It's the x values that are positive, so the x values have to be greater than or equal to 0, or I should say the x values have to be non-negative. Therefore, the x values have to be greater than or equal to 0. But to keep our y values positive also, we can't be using x values larger than 210. All right? So that's parts A through C. The parts that come after that, I won't show you the answer to the next one, but just for example, the question in part D is to find dp dx, which is the first derivative of our p equals equation from part B. So you do need to find the first derivative of that equation, and then part D also says solve the equation dp over dx equals 0. So whatever you get for your first derivative in part D, you'll then take that, set it equal to 0, and solve. And then the rest of the questions, or little sub-questions, play out from there. And I'm going to let you interact with those on your own. What do I want to look at next? Okay, so I want to go up here, and somehow I want to get over to the next question. Here we go. All right, question number 2 is a question about price. So the price charged for a candy bar is p of x cents. So the y value corresponds to the price charged for a candy bar. So what does our x value represent? X values represent x thousand candy bars. So if your x value is 5, then we're talking about 5,000 candy bars. So if we have x thousand candy bars being sold in a particular city, we're being told that the price per candy bar, p of x, is equal to 166 minus x over 10. And part A says find an expression for the total revenue from the sale of x thousand candy bars. Now, I'm an applied math guy, but I do work with a lot of problems that are sort of pure math. They're not necessarily applied problems. And they're definitely not all applied problems that are in the realm of business. So if you're new to the realm of business, you might not know either that in order to answer part A, which is asking us for an expression representing total revenue, and at the bottom of the screen you're seeing capital R of x equals, and you're thinking, capital R, I know that that means revenue, that's great. But where the heck did they come up with that equation as the answer for part A? It looks sort of like the p of x equals 166 minus x over 10 equation that we were given, the price equation or price function, but how did that become a revenue equation? The answer is that the total revenue from selling x number of items, or in this case x thousand candy bars, the total revenue is determined by taking the price per candy bar and multiplying by the number of candy bars sold. So in order to change lowercase p of x, in order to change that price function into a revenue function, we had to multiply by the number of candy bars, which is x. Well, sort of. X represents the number of 1,000 candy bars. So really, in order to change p of x into r of x, we multiplied by 1,000x. So if x were 5 and we sold 5,000 candy bars, what we're really multiplying the price equation by would be 5,000, not just 5. So again, Take p of x, multiply it by 1000x, and you will get your r of x equals equation. The questions that come after that should be very reasonable for you. The x value that leads to the maximum revenue. If we're talking about maximum, we're talking about taking the first derivative, setting it equal to 0, keeping in mind the critical value theorem. That will tell you whether or not you need to be checking the y values of your endpoints. In this case, are there really endpoints? None that are explicitly told to us. So my guess is, and you're going to have to find this out on your own, is why I'm saying that my guess is that you're going to need to take that first derivative, set it equal to 0, and solve. That's going to give you an x value, and I'm pretty sure that the part C asks you for the y value. And be careful of your units. Should you be answering using an x value that represents 1,000 candy bars? I'm going to leave it to you to double check. Does 830 in my example represent the total number of candy bars, or is it 830,000 candy bars? So be mindful of that when you're answering your version of this question. Just trying to smooth out the starting process for these questions so that you don't sit down and look at these questions and think, dude, I don't even know how to start these problems. How am I supposed to do this homework assignment? And you go and you look at the ebook and it doesn't give you enough clues, and then you're rooting around looking for other videos. So let me help you get these started. In this problem, a fence must be built to enclose a rectangular area of 20,000 square feet. Fencing material costs $1 per foot for the two sides facing north and south, and $2 per foot for the other two sides. And we want to find the cost of the least expensive fence. If you're finding the cost for the least expensive fence, does that sound to you like you're trying to minimize a cost function? Say yes. Okay, that is what we're trying to do. In order to minimize a cost function, wouldn't it be helpful to have a cost function? Say yes. Again, do we have enough information to create a cost function? I think we do. So those are the motions that I want to go through with you, is creating the cost function, and then I'm going to leave it up to you to figure out the answer to your version of this equation. Now, I need to pull up, because what we're looking at here is an active web page, so I can't draw over the top of it in its current state. So what I'm going to do is pull up a notepad off to the side, if it will cooperate here. That's not cooperating. There we go. All right. Let's get some more information on the screen here. And let's draw a little diagram. So our fence looks kind of like this. It's rectangular, and it has faces, or how does the question say this? Fencing material costs $1 per foot for the two sides facing north and south. Mm-hmm. So in the top right corner of your screen, I've written a capital N for north. So down here is south, west, and east. And I don't know how wide this fencing is from the top left corner to the top right corner. So it's running west to east. So I'm going to say that that has a length of x. And vertically, I'm going to say it has a length of y. And now let's see if we can use the dimensions, an x by y fenced area, to create a cost function. And let's just be kind of casual about this and write cost equals, now it's not area, it's just linear fencing to go all around this thing. The problem tells us that fencing material costs $1 per foot for the two sides facing north and south. So the upper fencing has a length of x. This lower bit of fencing has a width, or a length of x also. And vertically it has a length of y on the left side and the right side. So it's $1 per foot for the two sides facing north and south. So that's $1 times the number of feet of fencing that faces north and south. Not that runs north and south, but that faces north and south. So this side up here definitely faces north. This side faces south. So I would say that the total amount of fencing that's facing north and facing south is equal to x plus x, that north facing and south facing side, plus the cost for the sides facing east and west. Those are $2 per foot, and there are y feet of it on the left hand side of the rectangle and a y feet of it on the right hand side. So far my cost is equal to 2x plus 4y. Okay, what else were we told? Because this equation's got two variables in it, and that's making me nervous. The fencing must be built to enclose a rectangular area of 20,000 feet. Aha! So area, 20,000 square feet. We know how to find the area of a rectangle. We do length times width, or width times height, however you want to phrase it. In this case, it's x times y. Now, remember, we're trying to minimize the cost of building this fence while still maintaining a total area of 20,000 square feet. Minimizing cost. Need a cost function, preferably with only one variable. So here's what you're going to do. I'm not going to do this. You're going to do this. Because in problem number 1, we did this already. And now you're going to do this one. I'm going to take this equation. You're going to take that equation and make it say equals y. And then whatever that y value is, in this case it's going to be 20,000 over x, you're going to take that y value and you're going to plug it back in for this y right here. So you're going to have cost equals 2x plus 4 times your new y value, which in my version of the problem is 20,000 divided by x. Now I've got a cost equation that's entirely in terms of x, and you're supposed to minimize it. Minimize, first derivative, set it equal to 0, find that x value. Once you have the x value, you can use the area equation to find the y value. Then you'll have an x value and a y value that you can plug into the cost function in order to answer the question, the cost of the least expensive fence is. Now this question just as easily could have asked you for the dimensions of the fenced-in area. But they don't want that. They want us to do this kind of back substitution and end up actually figuring out the cost of the least expensive fence. Do you think that that's a reasonable, realistic, applied problem? I would say it is. It's not like a profit function or a price function where it's an estimate. If a farmer has a certain amount of area that they're trying to enclose, whether it's a farmer or it's just someone with a large piece of personal property, they want to enclose a large garden, and they want to minimize the cost of fencing, this is the kind of equation that they would want to know how to do, or that they're hoping that their kid neighbor knows how to do, or their son or daughter who's a college student. Boy, I hope they paid attention in their algebra classes and maybe their elementary calc class, and they can help me figure this out. You could potentially save somebody a lot of money by minimizing the cost. Certainly, conceptually, minimizing cost is a great idea. All right, so you're going to work on that and take a first derivative and set it equal to 0 and make sure you're finding a minimum. In the meanwhile, we're going to look at question number 4 that says that there's a candy box. It's made from a piece of cardboard that has those measurements. Squares of equal size are going to be cut out of each corner, and then the sides are going to be folded up to make a rectangular box. What size square should be cut from the corners, from each corner, in order to obtain maximum volume? You're not going to be putting a lid on this box. It's just going to have a bottom and the 4 sides, and you want to try to maximize the available volume. In the ebook, so this is specifically for my students as opposed to a passerby who happened to find this video, in the ebook, and it might be true for your book also, there's an example of this style of problem where you're maximizing volume with some illustrations. Now, if you're doing homework in my math lab, or perhaps you're using a different software if you're not one of my students, maybe you have a help me solve this button or a show me an example button. I can tell you I experimented the one that's available for this author's version of this book provided by this publishing company, and there were no illustrations in the example immediately available through the homework assignment. However, if you put your big kid pants on and put on your boots and make your way over to the ebook, you're going to find that there's a really nice example worked out that's going to give you a big assist with this particular problem. So I'm going to leave it to you to compare this problem to that problem and sort of mimic the procedures and processes gone through to solve the textbook problem and apply it to this one. And being that I'm making this recording in October of 2020, it's unfortunate to have an example problem, although it kind of hits home at the moment, where this one says that a disease has hit a city, the percentage of the population infected T days after the disease. So T is our independent variable. After the disease arrives is approximately P of T equals, etc. So P of T is percentage of the population. And we're being given a domain for our T values. It's between 0 and 35. After how many days is the percentage of infected people at a maximum? That would be very valuable. That would be that tipping point where you know that maybe you're starting to build some herd immunity and the maximum percentage of infected persons has been hit and we're going to start to taper and things are going to head back in the direction of normal. So that is always a good point. And if there were a really nice function like this one, where you could be doing some forecasting in order to determine when that turning point was going to happen, that would be some really reassuring news that you'd be able to share with people. So the percentage of infected people reaches a maximum after, in this case, 7 days. How was that determined? Take the first derivative, set it equal to 0. You're going to find a t value once you solve it. First derivative set equal to 0. And then if you take that t value and you plug it back into this given percentage equation, P of t equals 8t e to the negative t over 7. You take this number 7, in this case, the answer to part 1, plug it back into that P of t equation or function, and it's going to return a value of approximately 20.6, which has been rounded to the nearest hundredth. I'm pretty sure that you can handle taking the derivative of this equation, even though it requires you to use the product rule and the power rule and the chain rule. You've been practicing for this, so go in there and knock this out. Be very careful, be meticulous. I think you can handle this one. And for my students, we're actually going to be skipping the next section in the book. So for those of you who are in my class, I will see you in 6.4. Thanks so much.